We've been determining some tools to be able to determine convergence or divergence. So some of these tools that we're using to test these series for convergence or divergence are kind of some informal ones like these direct comparison tests where we can just compare term by term, typically with a known series like the 1 over n, the harmonic series, which is a divergent series. So if we kind of suspect that something's divergent, we may want to test it against a divergent series, or we can also test it, do direct comparison tests to a convergent series, such as the Basel series, which is 1 over n squared, which is convergent. So these are kind of a little bit informal, but these are some tools that we have to determine convergence, divergence. We're looking at a little bit more formal test, which is our limit comparison test. And our limit comparison test is basically checking the ratio of the terms, that a known term. So again, if we know it's diverging, we may want to choose a 1 over n function. And we're going to check this as a ratio of just the an terms. And basically what happens is when we check a known series versus a series that we kind of suspect is maybe going to behave the same way. So we have like Bn and compare it to a different one, Bn. What we want to see for this is that if we take a limit as n goes to infinity, if these terms then approach some limit, what that tells us is that these two series or these two sequences behave the same, and so the series will also behave the same. Okay, so if a over an is 1 over n and bn is some unknown sequence, and we do a limit of this comparison and we have a limit, we can say that since an is diverging, if an gives us a diverging series, the bn sequence should also give us a diverging series. So this is a limit comparison test. Now there's some limitations to this, so we want to have some more strategies, some more tests that we can use. So another new one that we're going to look at is number 3, and this is called the nth root comparison test. And the way it works is when we have a series and we have some terms in the series an, what we want to do is check the terms and see what's happening to the terms when we take the nth root of it. Okay, so this is what we do over here. We're going to take the nth root of the term inside the series, the an term, and we're going to let n go to infinity and see what happens. And if the limit is less than 1, we can say it converges. If the limit is greater than 1, we say it diverges. And then we have inconclusive evidence if it equals 1. Okay, so before, if we had when we did a test and we had the limit equaling 1 or some limit, then that would tell us something. But now, if we have a limit equal to 1, this is inconclusive. So what we're looking for is the limit of this test being less than 1. So where we might want to use this is when we have these series that look like this. So this is 2n plus 3 over 3n plus 2 to the power n. And anytime we have this type of series where we have the an term, okay, to some power of n, okay, this type of series kind of lends itself towards this nth root comparison test. I'm just going to make that a little bit bigger. So when we have some power on that of n, then they lend itself to this type of test. Because what's going to happen is when we test the terms, when we set this up, so it's going to look like this, the limit as n approaches infinity, and we're going to take the nth root of this 2n plus 3 over 3n plus 2, and that's going to be to the power of n. And you can see what is going to happen then is that conveniently, the n's are going to cancel out. Okay, we have an nth root, nth power, so they're going to conveniently cancel out. And what's going to happen then is we're going to end up with this equaling, well, this is going to be, and maybe I'm just going to put an extra step in here, the limit as n approaches infinity, the n's will cancel out, so we just end up with 2n plus 3 over 3n plus 2. Well, as the limit, we have the 3 and the 2, plus 3 and the plus 2 become insignificant. The ratios of the highest power n's are going to be compared, so we cancel those out, and we know that this is going to be equal to 2 over 3. Okay, so what that tells us then is that this is less than 1. So if we take a look at what we're going to conclude then, well, if it's less than 1, we know that this limit must converge. Okay, so less than 1, therefore, this is a converging series. Okay, so that's how it works. We just take, first of all, it lends itself to this type over here, where we have an n power, because the algebra works out nicely. And then the conclusion is, when we set it up and apply the limit, the conclusion is if it's less than 1, converging, greater than 1, diverging. If it's equal to 1, it's inconclusive. Okay. Now, why does this work though? Why does this work? So if we take a little bit more carefully, if we take a more careful look at this, if we look at this part, we have that part there and exponent here. And that's our an term. So I'm just going to write it over here. Our an term, okay, is really going to be some base, which is 2m plus 3 over 3n plus 2. That's the base of an exponential function, and we have the power n. This really is a geometric series. Okay, it's some base to the power n. And if it's a geometric series, all geometric series converge if the ratio, if the base is between -1 and 1. Okay, well, if it's between -1 and 1, we have a converging series. Well, what essentially we're doing is we are just looking at what happens to the base. What's happening to the base? As n goes to infinity, that base, or r, the r value here, in this case, the r value at infinite values, we're just looking at those, the r value becomes essentially 2/3, which means we have an r value less than 1. R values for any geometric series, when they're less than 1, okay, and actually I'm going to write the actual value in here. We know that if we had an infinite geometric series with an r value less than 1 like this, we know that these are converging series. These are converging series, because this is really just an infinite geometric series. Infinite geometric series. Okay, now although it's not quite a geoseries because there's n's inside the base, we are really just concerned with what's happening at infinity. And at infinity, those n's become not relevant, and we just really are talking about a base that's going to behave like 2/3. If the base behaves like 2/3 at large values, it's going to behave like an infinite geometric series, and therefore it must converge because of that fact. Here we have another example where we may want to apply the nth root test. And again, the indicator is the fact that we have a power n. Now, in this case here, this is an alternating series because it's -1 to the power n. And if you're curious about why we're starting at n equals 2, it's for the fact that if we put 1 in there, We have log 1 in the denominator, which means we have 0 in the denominator, and we can't have zeros in the denominator. So that's why it starts at 2. Now, this is alternating, and we'll talk a little bit more about these later, but I'm going to get rid of the alternating for now, because if it doesn't alternate and converges, then it will definitely converge when it does alternate, okay? Because if it's all positive and converges, if some are negative, some are positive, that should also make sure it converges because it'll have a smaller sum. So we're going to do this, just take the absolute value of this, and so we don't have to worry about that alternating -1 in the numerator. And because it's at nth power, that's an indicator that we may want to use the nth root test. So we're going to say the limit as n approaches infinity, and we're going to apply the nth root to this. So the nth root of, and this is going to be 1 over log n to the power n. Okay, those n's will cancel out. So we end up with the limit as n approaches infinity of 1 over log n. Okay, and when that happens, we can then evaluate this limit. We can put infinity in there, and that's going to be equal to 0. Okay, so if we think about what we're looking for, this is looking for this, the non-power n part to be less than 1, because it would mean it's an infinite geometric series with an r less than 1. In this case, that inside is not only less than 1, it's equal to 0. It actually tends to 0, not just a multiplier of less than 1, it becomes a multiplier of 0. So that's for sure going to converge. Okay, so we don't need to really worry about that. We could just use the fact that it is less than 1. It's less than 1. Therefore, we can make the conclusion, therefore, this is a converging series. Okay, and I put those absolute value in there, and we'll talk about that a little bit later, but I'm going to introduce some terms. And we're going to say that this converges absolutely. So because it converges whether it alternates or not, it converges absolutely, which means that for sure it will converge when it alternates.